So to compute the kernel for T, what we do is we start with the matrix 1, 2/3, 1/3, 0, 0, 0, 2, 0, and we get it to augmented matrix, which we can do by taking 1/2 R2, replacing R2, which gives us 1, 2/3, 1/3, 0, and 0, 0, 1, 0. Next, we take R1 minus 1/3 R2, replace it to R1, giving us 1, 2/3, 0, 0, 0, 1. Giving us the equivalent system of equations of A plus 2/3 B equaling 0 and C equaling 0. Now, what are our basic variables and our free variables? My basic variables are going to be A and C, well, not B, C, and my free variable is going to be B. Okay. So now, when we have this expression, I want to create the solution space. So let V be in the solution space, then V equals A, B, and C. And we're going to let B equal T, which is an element of the real numbers, because it's our free variable. Well, if we do that, then A equals minus 2/3T, and C equals 0. Well, what does this tell us? This tells us that V equals minus 2/3T, T0, which is T times minus 2/3, 1, 0, which is equal to, that's what V equals. So the solution space equals the span of the set of vectors minus 2, 3, 1, 0. And that vector is the coordinates of our basic, or our vectors in our kernel. And this is represented using the basis alpha. So if V is in the kernel of T, then V alpha is in the solution space. So to create our kernel, what we're going to do is we're going to convert our vectors here into what V is. So V alpha equals minus 2/3, 1, 0, implies that alpha, or V, sorry, equals minus 2/3 times 1 plus 1 times x plus 0 times x squared, or V equals x minus 2/3. So our kernel of T equals the span of the set of vectors x minus 2/3. And to look at our image, what we do is we take the free variables and we remove them and we look at just the basic vectors. Oh, our column space equals the span of the vectors 1, 0, and 1/3, 2. So now this is our column space, but each of these vectors represent a vector in our image. So V V beta equals 1, 0 implies that V equals 1 times 1 plus 0 times x. So V equals 1. And if V beta is our second vector, 1/3, 2, this implies that V equals 1/3 times 1 plus 2 times x. So V equals 2x plus 1/3. So my image of T equals the span of the set of vectors 1, 2x plus 1/3. And I get my image very nicely using this process and my kernel very nicely through the process, even though calculating what the null space of this might seem very intimidating, and calculating what the image of this operator might seem very intimidating. All we have to do is just follow our process. And we get what our image is, and we get what our span is. So now a basis for the kernel of T, it is the set x minus 2/3, and a basis this for the image of T equals the set, or is the set 1, 2x plus 1. And our rank of T equals 2, our nullity of T equals 1, and the rank plus nullity equals 3, which is equal to the dimension of the vector space V.